Welcome students to the MOOCs course on fuzzy sets, arithmetic and logic. This is lecture number 30. If you recall, in the last class I started with evidence theory. In fact, given a set X of alternative decisions, we have given three definitions: M, which goes from power set of x to 0 1. This is the basic probability assignment to a subset of x. Then we have defined belief of A to be sigma over M B, B contained in A, where A B belongs to power set of x. Then we have seen another function, plausibility of A, which is defined as sigma over M B. B is such that B intersection A is not equal to phi, and we have talked about Dempster rule for combination. In fact, it is combination of multiple evidences. We started working on a problem such that x is a set of three decisions A, B and C, two sources of evidences, M 1 and M 2, and we started working on computing their belief and also combining them. In this respect, we have come to this table, where the M1 evidences for different non-empty subsets are this, M2 evidences are this, and using the formula we have calculated the M1 to a combination of the evidences for different subsets of x. The formula for the combination was M12 for a set P is equal to sigma over M1 of set y and M2 of the set Z such that y intersection Z is equal to P. Let us look at the values. We have shown the computation of some of them. Let me just tell you how the M12 value for A is being calculated. M12 of A is equal to, we need to find out all those subsets whose intersection is going to be A. So, it is M1A multiplied by M2A plus M1A multiplied by M2 A union B plus M1A multiplied by M2 A union C plus M1A multiplied by M2 A union B union C plus M2A multiplied by M1 A union B plus M2A multiplied by M1 A union C plus M2A multiplied by M1 A union B union C. So, note that in each time the pair you are choosing, the intersection is going to be A plus M1 A union B dot M2 A union C plus M1 A union C dot M2 A union B. Thus, we have 9 pairs of subsets whose intersection is the singleton A. Therefore, from these values, when we calculated, the value of M12 for A is coming out to be 0.21. In a similar way, you can compute these values and all other values in particular. Let us now look at calculation of belief, since for each one of them we can calculate the belief. For illustration, I am just showing for one of them. So, let us compute belief 1 2 . So, we have M12, we already had those values, we are going to calculate belief 1 2 and we are also going to calculate plausibility 1 2. How to compute them? So, let us look at the set of non-empty subsets which are A, B, C, A union B, A union C, B union C and A union B union C. We had the values 0.21, 0.01, 0.09, 0.12, 0.2, 0.06 and 0.31. So, for your recall, belief of a set P is equal to sigma over m all those q such that q is contained in P. Therefore, what we will have? Belief of A is only m value of A, that is 0.21. Similarly, for B it is 0.01 and similarly for C it is 0.09. Now, let us consider A union B. For A union B, these subsets are A, B and A union B. Therefore, add these three values, we are getting 0.34. Similarly, for A union C, it is going to be 0.2 plus 0.09, which is 0.29 plus 0.21, which is going to be 0.5. And for B union C, it is going to be 0.06 plus 0.09, which is 0.15, 0.01, which is 0.16. And finally, for A union B union C, it is going to be the summation of all of them, which is going to be 1.0. Let us now compute plausibility. Can be computed in two different ways. One is plausibility of a set P is equal to sigma over m of q such that P intersection q is not equal to phi. And second one is that plausibility of P is equal to 1 minus belief of P complement. Therefore, plausibility of A is going to be 1 minus belief of A complement, which is B union C, and therefore, B union C the belief is 0.16. Therefore, plausibility of A is going to be 0.84. In a similar way, for B it is going to be 1 minus belief of A union C, and for A union C our value is 0.5. Therefore, for B the plausibility is 0.5. In a similar way, you can calculate here it is going to be 0.66, for here it is going to be, since it is A union B, we have to subtract 0.09. So, it is going to be 0.91. Since A union C complement is equal to B, therefore, we are going to get 1 minus 0.01 is equal to 0.99, and similarly, we can calculate for other sets. So, let us now compute plausibility using the other formula. And that formula is plausibility of a set P is equal to sigma over M of all the sets Q such that P intersection with Q not equal to phi. Therefore, we have x is equal to a comma b comma c. Therefore, plausibility of the set singleton A is equal to M12 A plus M12 A union B plus M12 A union C plus M12 A union B union C is equal to 0.21 plus 0.12 plus 0.2 plus 0.3 is equal to 0.84. Please notice one thing, these are actually subsets. So, when I am writing A union B, this is basically the set A comma B. So, here I have used the notation, but in these cases I did not use, but you have to keep in mind that union is between two sets. So, basically A union B is equal to singleton A union singleton B is equal to the set A B. In a similar way, plausibility of B is equal to M12 B plus M12 A union B plus M12 B union C plus M12 A union B union C. As you can understand that all of them have non-empty intersection with the singleton set B is equal to 0.1 plus 0.12 plus 0.06 plus 0.31 is equal to 0.5. Let me calculate one more for you. So, plausibility of A union B is equal to M12 of A plus M12 B plus M12 A union B plus M12 A union C plus M12 B union C plus M12 A union B union C. Again you can check that all of them have non-empty intersection with A union B, and this value is coming out to be 0.21 plus 0.01 plus 0.12 plus 0.2 plus 0.6 plus 0.31, which is coming out to be 0.91. You can now check with the values that we have computed. We find that it came out to be 0.84, it came out to be 0.5, this came out to be 0.91, and therefore, we can now calculate the plausibility value for B union C. It is going to be 1 minus belief of A is equal to 1 minus 0.21 is equal to 0.79. And as you easily understand that plausibility of the entire set X is going to be 1, because belief of phi is 0, therefore, 1 minus 0 is equal to 1. Now, let me give you some definitions. For any set P belonging to the power set of X, P is called a focal element of M if M P is greater than 0. This is because the non-zero basic probabilities are our concern. Therefore, we will focus only on those for which M P is greater than 0. Another definition is this set of focal elements along with their M values together is called body of evidence, and we denote it as F M, where F is the set of all focal elements and M is the basic probability assignment. Now, with the above definition, we go for some special case of evidence theory. Suppose the body of evidence is such that the focal elements are next. The focal elements are nested, then the corresponding theory is called possibility theory. So, let me first give an illustration. Suppose we have n elements in X and the focal elements are say x 1, x 1, x 2, x 1, x 2, x 3, x 1, x 2 up to x n. Then we can arrange them as follows. One set is x 1, the next set is x 1, x 2, the next set is x 1, x 2, x 3, the next set is x 1, x 2, x 3, x 4, and like that we have x minus 1. That means, the set is x 1, x 2, x 3 up to x minus 1, x 1, x 2 up to x n. I hope you understood the diagram. It is not mandatory that all the elements will have to be there. This is a simplest way of looking at it. One could have had x 1, x 1, x 2, x 3, then x 1, x 2, x 3, x 5. So, like that, if these are the focal elements, then also we could have got a nested sets, and that also would have given us possibility theory. The nested cases has one advantage, that belief of A intersection B is equal to minimum of belief of A comma belief of B, and plausibility of A union B is equal to maximum of belief of A and belief of B. This is very easy to visualize. In the example that I have given, let A be contained in B, strictly contained in B. Therefore, belief of A intersection B is equal to belief of A, since A intersection B is equal to A. And we know that as we are going to add one more element, with each addition the belief increases. Therefore, belief of A is less than belief of B, and therefore, belief of A intersection B is equal to minimum of belief of A and belief of B. We now prove the result for the general case. Let F equal to the set of subsets A1, A2, An such that each AI is a focal element. Also, as they are nested, we can order them linearly, that is A1 contained in A2 contained in A3 up to An, that is Ai is contained in Aj if I is less than j. Consider two arbitrary sets A comma B, which are subsets of the universe X. Let X equal to say 1, 2, 3 up to 10. Suppose F is as follows: A1 is equal to singleton 1, A2 is equal to 1, 2, 3, A3 is equal to 1, 2, 3, 6, A4 is equal to 1, 2, 3, 6, 7, A5 is equal to 1, 2, 3, 6, 7, 8, and A6 is equal to 1, 2, 3, 6, 7, 8 and 10. You can easily verify that Ai is contained in Aj if I is less than j. Let us take two subsets A and B of x. Let I1 be the largest index such that A I1 contained in A. Similarly, let I2 be the largest index such that A I2 is contained in B. So, example, A is equal to 1, 2, 3, 4 and B is equal to 1, 2, 3, 5, 6. Then if we compare with this, then I can see A2 is the largest index such that A2 is completely contained in A, and therefore, I1 is equal to 2 and A3 is the largest index such that AI is contained in B. Therefore, I2 is equal to 3. Note that for all j less than equal to I1, Aj is contained in A, and for all j less than equal to I2, Aj is contained in B. Therefore, Aj is contained in A intersection B if j is less than equal to minimum of I1, I2. Hence, belief of A intersection B is equal to sigma m of AI, I is equal to 1 to minimum of I1, I2 is equal to minimum of sigma I is equal to 1 to I1 m A I and sigma I is equal to 1 to I2 m of A I is equal to minimum of belief of A comma belief of B. Proved. One very interesting point with respect to nested focal elements is that belief is increasing. For illustration, consider two element case. A1 is equal to singleton x1 and A2 is equal to x1 x2. Therefore, belief of A 1 is equal to m x 1. Belief of A 2 is equal to belief of x 1 x 2 is equal to m x 1 plus m x 2 plus m x 1 x 2 is equal to m x 1 plus m x 2 is 0 because it is not a focal element plus m x 1 x 2, and we know that this is greater than 0. Therefore, belief of A 2 is equal to belief of A 1 plus some epsilon where epsilon is greater than 0. Therefore, we can see that as one element is added, the belief is increased. This is true if we keep on adding more elements such that focal elements are nested. Note the above is not true for a general case. In a similar way, plausibility of A union B is equal to 1 minus belief of A union B complement is equal to 1 minus belief of A complement intersection B complement is equal to 1 minus minimum of belief of A complement and belief of B complement is equal to maximum of 1 minus belief of A complement comma 1 minus belief of B complement is equal to maximum of plausibility of A and plausibility of B. Since in the nested case the function belief is called necessity and denoted as NEC, and plausibility is called possibility and denoted as POS. Therefore, we can write necessity of A intersection B is equal to minimum of necessity of A and necessity of B, and possibility of A union B is equal to maximum of possibility of A, comma, possibility of B. Since we have already seen in the last class belief of A plus belief of A complement is less than equal to 1 implies necessity of A plus necessity of A complement less than equal to 1, plausibility of A plus plausibility of A complement is greater than equal to 1. This implies possibility of A plus possibility of A complement is greater than equal to 1, and of course, the 3 is possibility of A is equal to 1 minus necessity of A complement. We may further observe one, minimum of necessity of A and necessity of A complement is equal to 0. This is because minimum of necessity of A and necessity of A complement is equal to necessity of A intersection A complement is equal to necessity of empty set, therefore, it is going to be 0. In a similar way, maximum of possibility of A comma possibility of A complement is equal to 1. This is because maximum of possibility of A and possibility of A complement is equal to possibility of A union A complement is equal to possibility of the whole set X, and therefore, since you are looking for an evidence from the entire set, this is going to be 1. So, thus possibility values in a nested case of body of evidence belongs to the set 0 to 1. In that sense, it is close to probability theory, but one major difference is that In probability, we assign values to each element, but here in possibility theory the values are assigned to different subsets of the universe, that is the set X, and that too they are nested. Let me now conclude the talk with the following theorems. Necessity of A is greater than 0 implies possibility of A is equal to 1, and 2, possibility of A is less than 1 implies necessity of A is equal to 0. Proof 1. Since minimum of necessity of A and necessity of A complement is equal to 0, therefore, if necessity of A is greater than 0, it implies necessity of A complement is equal to 0, since the minimum of them has to be 0. Therefore, possibility of A is equal to 1 minus necessity of A complement is equal to 1 minus 0 is equal to 1. Proof of 2, that is possibility of A less than 1 implies necessity of A is equal to 0. We know maximum of possibility of A and possibility of A complement is equal to 1. Therefore, possibility of A less than 1 implies possibility of A complement is equal to 1. Therefore, necessity of A, which is defined as 1 minus possibility of A complement, is equal to 1 minus 1 is equal to 0. Okay, friends, with that I conclude this talk. So, if we summarize what we have done, we have started with basic definitions of fuzzy sets and fuzzy memberships. Then we have looked at basic set operations on fuzzy sets and examined different properties of different fuzzy set operators. Then we have seen fuzzy numbers, types of fuzzy numbers, how to carry out arithmetic operations, on fuzzy numbers, how to order fuzzy numbers, how to approximate results of fuzzy arithmetic with triangular fuzzy numbers, etc. We have also examined different decompositions theorems, and the very important concept of extension principle. Then we have studied fuzzy logic, starting with propositional logic, we studied multi-valued logic, different logical operators, and inferencing from fuzzy logical statements. In inference, our focus has been on different types of logical statements, that is conditional, unconditional, qualified, unqualified, and also seeing how to infer from them. Then we have given a very practical approach namely Mamdani scheme. We have also studied fuzzy relations, and finally, the evidence theory or possibility theory. It was a long journey of 30 lectures, but I hope these 30 lectures have given you a very strong foundation of how to deal with uncertainty using fuzzy mathematics, fuzzy logic, etc. As I said in the very beginning that the concept of fuzzy came around the year 1965. So, over the last 50 years or so, the theory has been extended and many new concepts have come that I could not touch in the very introductory class, namely say in mathematics, people are talking about fuzzy complex numbers, fuzzy geometry, people also talk about inferencing, fuzzy systems, there are many other methods of inferencing other than Mamdani. In computer science, people talk about fuzzy automata, more advanced type of fuzzy sets, such as fuzzy set of type 2, intuitionistic fuzzy set, hesitant fuzzy set, also in different learning or in other applications, we can find use of fuzzy logic, such as fuzzy control, fuzzy data analysis, fuzzy clustering, fuzzy databases, and queries, etc. Also, people talk about fuzzy optimization, where constraints or resources are expressed in a fuzzy manner, like that. There are plethora of developments in the fuzzy set theory. It was not possible to complete all of them in a 30 lecture series, but again I say that if you follow the 30 lectures, you will have a very strong foundation of how to deal with the uncertainty using fuzzy mathematics, fuzzy logic, etc. With that, I conclude my series of lectures. I wish you all the success in life. Thank you very much.